The goal of this video is to use a very intuitive approach to showing how computers that only have ones and zeros manage to represent negative numbers. The purpose of this is to explore pointers, which is part of my bigger hobby of writing a C compiler and exploring how computers work. In the following videos, I plan to explore these topics to the point where we have a full intuitive understanding of everything about C pointers. When we use negative numbers in everyday math, obviously there's that negative sign that indicates whether a number is negative or not, and we have no way clearly to demarcate that. All we have to represent any kind of data are ones and zeros. The first and most obvious step is understanding that computers don't just see a 1 and a 0. They're looking at these ones and zeros in aggregate. They're chunking them. In the C programming language, we give different sizes names, and those names not only indicate how big they are, but also what they are intended for. What we use them for. In order to build up an intuitive understanding, let's go small. The smallest unit we'd normally deal with in a C program would be a char, or car, if that's how you like to pronounce it. We'll come back to chars, but I'm going to start with something simpler. I'm going to invent my own, even smaller data type. Introducing the nano, a very simple little data type, and it's very useless. Simple combinatorics tells us that we only have 4 representations possible with this small data type. When we program in C, if we're not worried about negative numbers, we can use the unsigned keyword. So if we put unsigned before our type, then it means we can use the full range from 0 all the way up to the full extent of the possibility of that number. So when we work purely in positive numbers, we've got 0, 0 representing 0. We have 0, 1 representing 1. We have 1, 0 that represents 2. And 1, 1 that represents 3. Right, so that gives us all the positive numbers. That's easy. The problem now, when we take away the unsigned keyword in our code, we are allowed to deal with numbers that go into the negative. And to do that, we use a system called 2's complement. And 2's complement was originally brought into use by computers in the days of von Neumann and the EDVAC, way back in the 1940s. Let's start building up to how it works. So if we have 0, 1 representing a 1, and we want to subtract 1 from that, we expect to get 0. 1 minus 1 is 0. So we need something in our black box to represent a minus 1. To do that, and to keep the CPU as simple as what we can possibly make it, it's already complicated enough, we want to use the arithmetic that the machine already provides us. If we do binary arithmetic, starting with the right hand side, if we add a 1 to the 1, that will give us a 0, the 0 that we want, but it gives us a carry. Because of that 1, we'll want another 1 there, which gives us another 0 and another carry. Now the good thing of this system is that our data type is only 2 bits wide, and so when we add that additional 1, it just falls off the end and disappears. What this means is when we tell the computer to do signed arithmetic, 1, 1 becomes 3. If you remember this slide, you'll see that our 3 has now become our minus 1. So these become all the numbers that we have for this data type when the data type is unsigned, as in it's positive. And then when we have signed, in other words, it can be either negative or positive, these are the numbers that we have. That gives us a good start to the beginning of the logic of how to do this, but we need to look at bigger numbers to get an intuitive sense about how this works. To do that, let's go back up to our char type. Normally in C, we think of the range of char types as the ASCII table, but of course, just like everything else, they're just ones and zeros. They just happen to be 1 byte or 8 bits, and so we have 8 boxes to absorb magnitude, and giving us a full set of values that we can range across up to 256. I'll show you a couple problems and then we'll move on to some shortcuts. In this example, we have 7 on top because it's 1 in the 1's column, 1 in the 2's column, so that makes 3, and 1 in the 4's column. 3 plus 4 is 7. So in the next row, we want to figure out what do we need in order to arrive at zeros at the bottom. So by following the same logic that we used before, we can see on the right hand side we need to add 1 so that we get a 0, and then it's going to do some carries, so we don't need a 1 for the next one, we don't need a 1 for the next one, but then the following one where there's no 1, at the top, we do need a 1. So essentially we need the opposite all the way except for the first one. In this example, essentially what we've done is flip the bits and then added 1. That works when the numbers have a 1 all the way to the right hand edge. Let's look at an example in which that's not the case. So in this example, we've got a 1 in the 2 to the 2nd column, that's a 4, and 1 in the 2 to the 8th column, which is an 8. And so that gives us a total value of 12. So if we start with the first 2 columns, we've got zeros in them, and so we can just make those a 0 because 0 and 0 makes 0, obviously. The first time that we'll need a 1 is only in the 3rd column. An easy rule to make then is that we keep everything the same until the first 1, and then we flip everything else. And that's it. So there's 3 things to note. The first is all the problems that we did, we ended up trying to solve for 0. Why solve for 0? Because if we solve for 0, we find the negative of the number that we've got. If you have an 8, that solve for 0 and you get a negative 8. So you can always find the representation of a negative of a number by solving for 0. The second thing to note, especially if you do work in assembly language, is that the representations for negative are numbers that would be used for the representation for positive, as we saw with the 3 and the negative 3. And so that means that there's fewer numbers available. If you think of n as an exponent, n being the number of boxes we have in the magnitude, to the power of 2 would be the total number of unsigned variables that we have. But as you can see from the formula, if you take a second to have a look at it, it's fairly easy. We end up with fewer values because we've used up a bunch of them for the negative numbers. And the third and final thing that's interesting is that the leftmost bit becomes a signed bit. In other words, when we're dealing with signed numbers, negatives and positives, if you look at the leftmost bit, the highest value bit, it's going to tell you whether it's a negative or a positive number. Negative numbers will always have a 1 in that box. Positive numbers or 0 will always be a 0. I'm well aware that this is quite a niche topic, and I'm not sure that many people will be very interested in it. And I'm not even sure that I teach it very well, but it's something that I'm very interested in, and I look forward to doing more videos of this kind of stuff. I'm really interested in low-level computing. I'm finding it more and more fascinating the more time I spend doing it. Hopefully some of you feel the same. I'd love to know. If you do find it fun, I'd be really thrilled if you leave a comment, give me a like, and subscribe if you want to see more of it. I hope you have a super day further, and thank you so much for watching my video.